Hello everyone, and welcome to today's webinar. Thank you for joining us today. My name is Haruka, and I'm the application specialist at Salink Kyoto. Today, we have a webinar with Dr. Charles Tsai, CEO of Saitena Bioprocess Solutions from Taiwan. He's going to talk about our exciting new product, CBARD. Before we get started, just a little housekeeping. So since all the audience is muted during a presentation, if you have any questions during presentation, please type them into the question box in your GoToWebinar control panel. Myself and my colleague will try our best to answer your questions, and we will also have the time for questions at the end of the presentation. After the presentation. And also we will have polls during presentation, so please select your answer on your screen. So I think that's all from me. So Charles, please go ahead and start.
Okay, so thank you, Haruka. And hello, everyone. Thank you for attending the webinar today. I'm Charles, and I'm very happy to be here and give an introduction about CBARD technology, which will be the next revolution of cell culture. And there will be a Q&A session at the end of the presentation. So feel free to type your question as we go along, and we will try to answer it during the Q&A session as well. Okay, so I believe all the scientists understand the importance of the mixing for cell culture. And for a traditional steady culture, cells are limited in the 2D growing space. Oxygen also comes from the gas-liquid interface, which is at a far distance to the gas-liquid to the cells. All the waste metabolics that the cell produce are also concentrating around the cells. So this makes an ideal cell culture environment. So if we enable the mixing culture, the suspension cell line can have a 3D growing space. All the cells can have equally distribution of the oxygen and or the nutrition. So even for the adherent cell line, it can also refresh the medium surrounding the cells as well. So the mixing culture is really benefit for all the cell cultures, even in a small scale. And here is the cell line development process published by the well-known pharmaceuticals companies. So cell line development process typically starts from a single cell culture, probably in a 96 well plate, and continuously scaling up to 24 well plate or 24 well deep well plate, and then ending up with some kind of shaking flask or bioreactor. And as you might already notice that mixing of the cell culture only begins from shaking flask or 24 deep well plate, and all in the later stages. However, in the first two stages, 96 and 24 well plates, current technology in the market do not enable mixing culture. Therefore, pharma companies can only do the steady culture, which is not ideal cell culture method. This is where CBARD plays a revolutionized role. CBARD wants to fulfill this gap to enable suspension mixing culture in the 96 well and also 24 well stage. So 3D suspension environment for small-scale cell culture is what CBARD wants to achieve. And CBARD, one CBARD system can consist a docking station and 3 control units, which can operate 3 96 and 24 well plates. And the CBARD working principle is quite simple as well. There's a CBARD lead. There's a CBARD lead which can feed with a standard 96 well plate. And there are 96 tubes which can be inserted into all the wells of the well plates. And the steamer control units can be docked right on the top of the steamer lid to pumping up and down the medium in all the well, somewhat like a multi-pipetting system. So as shown in the video, here you can see medium can be like this, pumping up and down by supplying the suction pressure and pumping pressure to do the reciprocating mixing in all the wells in parallel. And as shown in the video, in the right hand side here, so I'm not sure. Sorry, give me a second to play this video. I can yeah. So as shown in the video on the bottom right on the slide, we can have placed a camera at the bottom of the well, which steamer is operating. And you can see that the choke one cells are being pumping up and down to all in the wells, and all the cells can be resuspension and keep the suspension inside all the wells. Okay, and I will now share some data of silviculture in the following slides. This will help you to understand the difference that silviculture can bring to your cell line development process. Okay, before showing the data, I would like to point out that silver enables customizable mixing option. While mixing is generally good for cell growth, but too much mixing may be detrimental for a very low cell density. So for example, from a single cell level to around 1,000 cells per milliliter, we define as a low cell density. So even in this low cell density, we can still offer periodic mixing. For example, every 3 hours, you can mixing for only 10 cycles, which you can done by this kind of periodic mixing setting. And for a higher cell density, from 10 up to 4 to 1 million cells per milliliter, that's we call higher cell density, and you can use continuously mixing, which is continuously pumping up and down of all the wells. And we recommend continuously mixing of the cell culture for most optimal growth. The mixing conditions can be tailored to your needs and the cell types. And there's a poll to just to let me know. We share questions that to let me know what kind of cell density you are actually working on. We are quite interested in of this part. So I will wait for a few seconds to let the audience to fill up the poll, the question pool. Okay, I think most of the audience has filled, so I can continuously for the cell data. And so in this experiment, we look at the cell growth and the protein yield of the CHOK1 cell line that produces HER2 antibody used for the treatment of breast cancer. We compared SIBR to the steady culture in the 96 well culture plates and took an endpoint measurement. And in the case one, we seeded 500,000 cells per milliliter and culture for 5 days. And in the case 2, we seeded 1.5 million cells and culture for 3 days. And as you can see from the charts on the right here, the SIBR consistently produced much higher cell density and antibody protein yield compared to steady culture in both case 1 and the case 2. And SIBR also produced a higher QP value, which is productivity per cell per day compared to the steady culture. The experiments showing that the SIBR culture provides more optimal cell growth for higher cell density and the protein yield. So as you can see from the figure here, the cell density can be 2 to 3 times higher, and the retained protein yield can be even 3 to 4 times higher. So the concept is quite simple, that you make cell growth in a healthier, better environment. It should be has a better behavior. And the second data is actually generated by our customers. So it's CHOK1 cells, but the title is remain unknown because it's a secret from customer. And they seeded the cells at 3 different density, which is indicated here. So the seeding density is, there are 3 different seeding density. And they compare SIBR and the steady culture for cell viability and density after 3 days of culture. So it's also endpoint measurement. At the lower cell density, SIBR do not differ greatly from steady culture in terms of cell density. However, at a higher cell seeding density, SIBR enable much higher cell growth up to 5 million cells per milliliter with 98 cell viability. So steady culture only has 1.3 million cells per milliliter and with only 84 viability. So this experiment shows that the SIBR can strengthen growth potential of cell culture when steady culture reach its limit of a 2D growing space. But SIBR can even push it to higher cell density. So as you can see the figures of the SIBR can make the cell density even higher to 5 million cells per milliliter. And you can also find the result from this slide as well. We also did correlation assay to see how well SIBR compared to a shaker condition. We compare SIBR and the steady culture, also the 125 milliliter shaking flask with 30 milliliter cell suspension, and under the condition of 150 RPM shaking, orbital diameter is 90 millimeters. And we measure the cell density every day for 5 days, and you can see that the cell density of a SIBR and the shaking group are quite similar, but the steady culture group can only remain at a lower level here. And this shows that the cell growth in SIBR condition mimics the growth rate of the cell growth in the shaker flask. And the same goes to the doubling time and also the viability. You can see when the shaking flask dropping down of the viability, SIBR is also have a similar behavior. And also for the doubling time and the titer measurement, you can find out from the figure that SIBR always have a similar result as shaking flask, but not a steady culture. This is extremely important for early selection of the cell clones, which save time and the cost for the cell line development process. So the data shows us that SIBR culture condition is much more representative at the later stage shaker flask conditions. And we also measure the oxygen volume at the bottom of the well. The data shows that the SIBR condition increases oxygen level at the bottom of the well. As you can see in the figure, the gray curve is only pure midland without any cells inside. And the blue curve is steady, dark blue curve is steady cell culture. And you can see the oxygen level dropping down very quick after 2 hours of the culture. The sensor is being integrated at the bottom of the 96 well plate. So it's indicated the bottom of the 96 well plate. And the SIBR cell culture, even with not the most missing setting, it still can remain a relative higher level of the missing. And This is important in preventing hypoxia in cells, which may be important for some of the researchers as well. And we can also show that SIBR has no cross-contamination issues. One of our customers tested this by intentionally only adding cells to row A, C, E, and G, and continuously culture for 7 days. And after 7 days, they only see cells still in a row A, C, E, G, but there's no cells to a row B, D, F, H. At the same time, they also measure the titer production. And as shown in the figure, SIBR performs higher titer than the steady culture, so close to 3 times more for the SIBR culture and steady culture. And some of the people probably question about why there's a pattern like this. So it's actually they put the plate on the centrifuge. So the pattern is generated because of the centrifuge, not the SIBR mixing. And here is low cell density. It's actually quite interesting experimental setup. It's also a little bit complicated. And this slide shows example that SIBR can also have benefit for low cell density. In this experiment, our customers seeding single cell into 6 plates and separate it to SIBR group and the steady culture group. So each group had 3 plates. And for a SIBR group, first day 1 to day 10 is still remain steady culture because the customer wants to take some picture of the single cell clone, which has to be requested by FDA. And from day 11 to day 14, we start to using SIBR mixing. Actually, it's a periodic mixing. So for this case, people, the customer only using every 20 hours to mixing for 10 cycles, because for their cell line, the doubling time is around 20 hours. And then they pick up the top 12 clones and to measure the titer. And for a steady culture, from day 1 to day 14 is all remain a steady culture, and then they still also pick up the top 12 clones and measure the titer as well. And as you can see the figure, in this stage, a SIBR still has a better performance in this average of the top 12 clones. And then they continuously scaling up these top 12 clones to the 6 well plate shaking culture, and then measure the titer again. And SIBR still can have a better performance. And so basically what the customer thinking is like SIBR has somehow with a pre-salivation impacts to their cell growth. Okay, so one set of SIBR, as I mentioned before, one set of SIBR microbial includes 1 docking station and 3 control units. And for one laptop, you can connect in to 3 to 5 sets of the SIBRs. So it makes you with, if some people want to do a high throughput, it's still available with our system. And the whole device is very compact and able to put it into an incubator. And we only need 1 single USB cables to come out from the incubator and to connect into the laptop for power supply and also data transfer. And for the missing level, missing rate is also adjustable to fit different type of the cell line. Even you can set up like a periodic mixing as well. And the consumable is a one-time use consumables, of course, and is sterilized and very well packed. And currently for the 96 well plates, it fit with a standard 96 well Eppendorf cell culture plate, as there's a special design to prevent the evaporations happens during the mixing. But also we understand some of the customers want to use differently for different plate, for example, Corning or different brand of the 96 well plates. So we can also still offer a customized for your plate as well. But for now, the standard is for Eppendorf cell culture plate. Also, for a 24 well plate version will be available very soon in this year, later this year. Okay, so today we only focus on the cell line development market for the data. But there are potentially to use in different applications as well. We have been asking from different fields, such like a stem cell, cancer cell culture, or microbiome yeast culture, cell therapy, medium optimization, and so on. So just let us know what kind of field you are currently working on. Then we have a better understanding of what kind of field people are in this webinar. Okay, and okay, so that's basically my talk for today. So feel free to also drop me an email if you have any questions, or you can type your question in the Q&A session as well. Thank you.
Thank you, Charles. Okay, so let's take some time for questions, to take some questions. So yeah, all the participants, please be sure to type your questions into the question box in your control panel on the GoToWebinar. So I actually have a few questions. May I start, Charles?
Yeah, sure.
Okay, the first question. Did you observe any evaporation issue during the seabird mixing culture?
You can probably imagine that if you increase in the mixing rate, so the evaporation issues will be also increased for sure. And then, so that's the reason why we choose the Eppendorf cell culture plate currently, because there's a special design. You can add PBS into the mold, which is surrounding the wells. And then that do helps to prevent evaporations issues inside our system. And currently, basically, the SIBR system can enable the scientists to continuously run for 2 weeks without critical evaporation issues here.
Thank you. I see. Okay, so another question. How long could a seabird operate inside the incubator?
Yeah, that's what I just mentioned. Basically, seabird has special design to prevent our humidity and also gazing into our electronics devices. And so in theory, you can run forever for the seabird to put inside incubator, but also as mentioned the question before, there's evaporation issues. And so if the evaporations make a whole place dry, then the system may stop mixing. So you can also recognize an indicator that when the evaporation getting critical for your well place as well. So basically, in summary, our device is without any issues to run inside the incubator, but evaporation will be critical after 2 weeks of the culture. But most of the customers won't really culture for more than 2 weeks, as far as I know.
I see. Okay, thank you. Another question. One of the audience, the purpose, his or her purpose is express and purify the recombinant proteins. So how much amount of protein can he or she get in a 24-well plate?
It's actually really depending on different cell lines. But as you can imagine that if you push the cell density higher, so you will get more protein yield definitely. So in our 24-well plates, we also have similar result than the 96-well plates as well. So right now, normally we can get 4 to 5 times higher than a steady culture. So whatever you are right now culture in the steady culture, right now you can get even more up to 4 to 5 times, and it's a more high throughput inside the 24 or 96 workplace.
Thank you.
Okay.
I do not see any other questions. Does anyone have any other question? Oh, okay, here. So what kind of transaction method do you use for CHO-K1?
Actually, this question will remain unknown because our sales line is always come from the customer. So the transaction method right now, we didn't really check with the customer what kind of transaction method they use, but it should be a standard industrial method because they all using for COD market, and the sales line is always using for industrial standard.
I see. And it's sometimes tricky to reveal all the information, so I understand.
Yeah, exactly. So all the pharma customers are really careful to disclose all this information.
Yeah, I understand. Thank you.
Mm-hmm.
Okay. Anybody else have any question? Charles, do you have any other information or any other things that you'd like to mention or share?
Yeah, so basically, in current version of the CBER is only with missing function, but we are also still working on to integrate different sensors. So I probably understand some of the scientists also interested to monitor, for example, dissolved oxygen or pH value inside the 96 workplace or 24 workplace. And just want to let everybody know we are working on this, and it will be available very soon, in the future.
That's very exciting. That's really cool. Oh, I got another question. What are the other cell lines that the people can use for expression and purification?
Okay, so I would say every kind of cell lines might be interesting to using CBER, as I mentioned in the very beginning. That of course we are currently focusing on the suspension type of culture, and that means we would like to make cells into suspension. But also we hear some voice from different application fields, which probably using adherent cell type. And adherent cell type don't want to make suspension happens, right? But some of the cell lines are facing hydroxia situation, or they just want to make cells not to be crowded together, want to separate it a little bit, separate from each other. And also for this kind of continuously missing, if you make the missing rate very low, you can make sure the cell won't go into the suspension. And at the same time, you can still refresh the medium to bring the waste away from your cell line. So basically, we haven't tried a lot of different cell line because we just launched CBER recently, but we are very open to testing different cell line and to broaden our application in different kind of cell culture. And right now, as I mentioned, we already get some requests from, for example, yeast culture or a microbial culture, and also cancer or stem cell culture. We also realize that there are more application than we expect.
I see. How about you briefly mentioned about to the adherent cell types? How much applications are there currently in adherent cell?
Currently, mostly is interesting about actually cancer cell culture. So normally for a stem cancer cell culture, people always face a little bit like, for example, the growth rate is not good enough, or the sales is limited. So they have to be very careful with their cell lines, and they want to grow the stem cancer cell line more. That's mostly we find out for cancer cells. Also for a spheroid culture, there are also trends that people are asking about.
I see. Yes, spheroid will be very, very interesting as well.
Mm-hmm.
Okay, I think. Yeah. Any other questions? Okay, so maybe I will make the, oh, actually I got a question. So this person is growing a HeLa adherent cells, and they do not grow in suspension.
Yeah, so that's the things I mentioned. We can actually using CBER, but not really, make cells into suspension as well. So you just make a gentle mixing, and you can make oxygen level higher in the bottom of the well. So I believe this kind of HeLa cells, adherent cells, may have some bad impact when they get in crop.
I see.
Yeah. Okay.
Okay. So, Charles, did you conducted all the polls? And
Yeah. So here.
Okay, sounds good. Okay, I'll make announcements. So we have more upcoming webinars in different languages as well. We have one in French, we have another one in Spanish, and also we have Fresh 3D bioprinting, closing the gap between structure and a function in bioprinting by Andrew. And the one that is relevant to APEC time is in August 26th, Bioink Development for Stem Cell Engineering by Professor Chu Gu. And also the next slide. So if you are interested in a demo, please contact us. I think people are now going back to the lab. And so please contact us for if you're interested in demo. Oh, just sorry, Charles, one more question. I just have one more question here.
Okay.
Before we go. Okay, so this person'd like to use, so whether if there's any other function to control culture condition, for example, pH control, feeding more liquid, and so on.
Yes, it's also under our development roadmap. But it's obviously it takes more time to develop, but it certainly will be our next generation. We were trying to integrate all these functions. Right now, we can for sure tell you the monitoring functionality will be already integrated into the next generation of the product.
Great, thank you. Okay, so maybe we'll wait. Oh, another question. Okay, so okay, so this one, so for the demo, we'll contact individually after the this
webinar. Yeah.
Session, yeah, webinar, yeah. So perfect. Yeah. So if you're interested in demo, please contact us, and we'll schedule. We'll do the demo. Okay, I think this is it. So thank you again, Charles, and thank you everyone for joining us today. If you have any other questions, if you'd like to have a demo, please contact us. And if you're interested in other webinars, please sign up for the webinars. And yeah, thank you again. And I wish you all a great rest of the day.
Yeah.
Happy
Thank
Wednesday.
you very much for today. Thank you. See you.
Thank you. Bye.